Hello and welcome to this next lecture on pattern recognition. We started discussing the support vector machines from last class. As we already discussed, this is an approach where the idea is that we effectively transform the feature vectors into a high dimensional space and learn a linear classifier there, because you already know how to learn a linear classifier, and learning linear classifier is in general more efficient. We want to learn a linear classifier in a high dimensional space, which in the original space will be a nonlinear classifier. That is the basic idea. And we said that for the idea to work, we actually do not learn any linear classifier, but learn what we call an optimal separating hyperplane. Okay. So, to briefly review, we have been discussing the SVM method, and the one major new concept is the optimal hyperplane, right. We formulated the optimization problem of how one learns optimal hyperplane. We seen that for learning optimal hyperplane, we essentially have to solve a quadratic optimization problem with linear constraints. We basically, the optimal hyperplane is one which maximizes the separation. And we looked at the formulation only under the assumption that the training set is linearly separable. That is the case we have been considering so far. Okay. So, what we will do in this class is we quickly review we start with the optimization formulation again, quickly go through the dual, and then move on and see how we can do the same formulation in general, even when the training set is not linearly separable. So, the optimal hyperplane is a solution to this optimization problem. What is the optimization? It is a constraint optimization problem, namely to minimize W transpose W subject to 1 minus y I into W transpose x I plus b less than or equal to 0. Optimization variables are W and B, right. Find W and B to minimize half W transpose W subject to these constraints. What does this constraint imply? As you already seen, if W comma B represents a separating hyperplane, then y I into W transpose x I plus b will be equal to 1, will be greater than or equal to 1. So, essentially y I into W transpose x I plus b greater than or equal to 1, which is same as 1 minus y I into W transpose x I plus b less than or equal to 0, tells you that this W b is a separating hyperplane, and a separating hyperplane such that W transpose x I plus b is equal to minus 1 and W transpose x I plus b is equal to plus 1, the two parallel hyperplanes that we considered last class, no pattern is in between. So, a separating hyperplane for which the margin of separation is given by 1 by norm W, that is any W b that satisfies this constraint will be a separating hyperplane for which the closest pattern is 1 by norm W away. Hence, among all such W b, if I minimize this, then I am finding a separating hyperplane which has the maximum margin of separation, meaning the closest training pattern is far away for this hyperplane compared to any other separating hyperplane. So, that is why it is a constraint optimization problem. Among all separating hyperplanes, that is all W by satisfy this constraint, find the one which has the maximum margin of separation. Okay. This is the optimization problem. So, the optimal hyperplane is a solution to this problem, and this is the cost function. So, which is quadratic, convex quadratic, all constraints are linear. So, this is the most efficient constraint operation problem one can solve. For this problem, because this is convex and the constraints are linear, Kuhn-Tucker conditions are necessary and sufficient, every local minimum is a global minimum. We have seen all the background of constraint optimization last class. So, let us quickly write down the Kuhn-Tucker conditions for this problem. Okay. Before that, let me give you the I have been telling you that these constraints essentially mean that if the hyperplane is at the center, then on either side I have got these two parallel hyperplanes, and this is the margin of separation. So, what the optimal hyperplane is doing is that finding that hyperplane which has the highest margin of separation. That is what my optimization problem is. I do not want a separating hyperplane like this, but I want a separating hyperplane like that. A separating hyperplane for which the closest pattern is more distance away than this. So, this is a non-optimal hyperplane, whereas that is a optimal hyperplane. Okay. So, what is my Lagrangian for this problem? So, Lagrangian is my cost function plus sum of all the constraints into Lagrange multipliers into constraints. So, my Lagrangian will be half W transport W plus sum over I mu I into 1 minus phi I W transport x I plus B. Mu I are the Lagrange multipliers. So, is a function of W B the optimization variables and all the mu I which are the Lagrange multipliers. So, what are my conditions? The gradient of L with respect to the optimization variable should be 0. So, if I equate gradient with respect to W to 0, if I take W gradient, I get W here, and from here there is one linear W term. So, I get mu I y I x I. So, essentially at the optimal W star is summation mu I y I x I. For all the optimal variables we put star. So, mu I star is the optimal values of the Lagrange multipliers, W star is the optimal value of W, the normal to the subtending hyperplane. So, from gradient of L with respect to W is 0 gives me that W star is this. Gradient of L with respect to B 0 gives me there is only one B term but that is linear. So, I get I is equal to 1 to n mu I y I into B. So, differentiate it, I get summation I is equal to 1 to n mu I y I is equal to 0. This is the condition that the gradient of the Lagrangian with respect to operation variables is 0. Then we need feasibility. So, all constraints should be satisfied. So, 1 minus phi I into x I transpose W star plus B star is less than or equal to 0 for all I, and then I have complementary slackness. So, first I want all the Lagrange multipliers to be positive or non-negative and mu I star into the constraint. Okay. As I have already mentioned last class, our optimization problem is such that there is one constraint for each example. Essentially, because I want WB to be a separating hyperplane, for each XIY, each example XIY, it should be on the right side of the separating hyperplane. So, each constraint is tied to one example, each example has one constraint. So, each constraint is the corresponding xi. In my Lagrangian, each constraint will have its own Lagrange multiplier. So, my each Lagrange multiplier is tied to a particular example. Okay. So, I can talk of Lagrange multiplier for that example, because each Lagrange multiplier is for a constraint and each constraint is for an example. Now, this complementary slackness gives us something very interesting, as we see in last class. Let us say S is the set of all indices for which the corresponding Lagrange multipliers are strictly positive. You know, Lagrange multipliers have to be greater than or equal to 0, some of them might be 0, some of them might be strictly positive. S may be the index such that Lagrange multipliers are strictly positive. Then the complementary slackness says if this is strictly positive, this is strictly greater than 0, then this has to be 0 because the product has to be 0. So, if I belongs to S, then y I into x I transpose W star plus B star equal to 1. What does this mean? This means that the xi is on the hyperplane W star transpose xi x plus b is equal to plus 1 or minus 1, depending on whether y is plus 1 or minus 1. So, is on one of the two parallel hyperplanes, which means that xi is a pattern that is closest to the separating hyperplane. So, the xi corresponding to the non-zero Lagrange multipliers or the training patterns which are closest to the separating hyperplane, right. The complementary slackness says if mu I star is greater than 0, then this has to be 0, right. So, if I think of S as the set of all Lagrange multipliers, indices of all Lagrange multipliers which are strictly positive, then for all those I know this is satisfied, which means all the corresponding xi are closest to the separating hyperplane. We will call such xi corresponding to positive Lagrange multipliers as support vectors. These are training patterns that are closest to the separating hyperplane, and these are my optimal W star I already know is summation or I mu I star y I x I. So, if the summation need be taken only over those mu I star which are strictly greater than 0. So, essentially my W star is a linear combination of the support vectors, if I define this as the support vectors, right. Also another thing that should be remembered is that for my optimization problem, if mu I star is equal to 0, then the constraint is not active. So, which means essentially these xi corresponding to the support vectors are the critical xi, because if I take away all the other examples and leave only these, I still get the same separating hyperplane. The optimization problem will not change. Okay. So, W star is a linear combination of support vectors. We have already seen while discussing perceptron that any separating hyperplane will be a linear combination of xi, but for the optimal separating hyperplane is a linear combination of some of the xi, not all, only the what we call the support vectors, and the linear combination involves the corresponding Lagrange multipliers. So, optimal W is a linear combination of support vectors, right, and in this sense support vectors constitute a very useful output of the method, right. For this problem, so these are the support vectors, the patterns that are darkened, they are closest to the separating. So, as you can see geometrically, if I throw away all the remaining data and just keep the support vectors, right, for that pattern classification problem also, this will be the best hyperplane. So, in some sense support vectors are the most critical examples of this pattern set, of this example set. Thus, as we shall see later on much more clearly, support vectors constitute a very useful extra output of the method in addition to getting the W star like this. So, let us sum up the SVM solution. SVM tries to let the optimal hyperplane. Optimal hyperplane is defined to be one that maximizes the separation, is a separating hyperplane which has the maximum separation. The optimal hyperplane is given by W star transpose x plus b is equal to 0. Then the W star and B star are given by this. W star is summation over I mu I star y I x I, and B star, how do I know B star? From the complementary slackness. Whenever mu j star is greater than 0, I know y j into x j transpose W star plus B star is equal to 1, right, because my complementary slackness tells me that whenever the mu is Lagrange multiply 0, this is equal to 1, right. When this is 1, we multiply both sides by y j, remember y j square is equal to 1 because y j is plus 1 or minus 1. So, that gives me B star is y j minus x j transpose W star. Okay. So, once I have all the mu I stars, I can calculate W star, and I can calculate W star and have all the mu stars. I can take any j such that mu j star is greater than 0 and B star will be this. Theoretically, no matter which j you take, you should get the same value of B star. Okay. So, thus W star and B star are determined by your mu I stars, your Lagrange multipliers. So, if I can get the optimal Lagrange multipliers for this problem, I am done, and because I essentially want to get Lagrange multipliers, one way of solving this problem, one way of getting the optimal hyperplane is to find mu I star by solving the dual of the optimization problem. We see in last class how to find the dual. For the dual, we find the dual function which is the infimum of the Lagrangian and then maximize the dual function, right. So, what is the dual function for this problem? Is a function of the Lagrange multipliers q of mu, which is infimum over the optimization variables W b of the Lagrangian of W transpose W plus I is equal to 1 to n mu I into 1 minus y into W transpose x I plus b. Okay. I have to find infimum of this with respect to both W and me. So, for a given mu, I have to find infimum of this with respect to W and me, that becomes the value of q mu. So, ultimately I get a function of mu, and that is what I have to maximize subject to some constraint, the constraint that mu i's are positive, that is what the dual is. Now, if I want to find infimum, first notice that there is a term here, summation I is equal to 1 to n W I, summation I is equal to 1 to n mu I y I b, with a negative sign in front, but that does not matter. So, there is a term here, that is b times summation I is equal to 1 to n mu I y I. Now, I am finding infimum with respect to b. So, if summation mu I y I is not equal to 0, then infimum with respect to b minus infinity. I can take b to be sufficiently large, positive or negative as the case may be, to keep decreasing q mu, right. So, if summation for a given mu, I am finding the value of q at a given mu. For a given mu, if summation mu I y I is not equal to 0, then for that mu, the value of q mu will be minus infinity, because the infimum minus infinity. I am not interested in those mu's, because I am maximizing q mu. So, mu at which q mu takes value minus infinity is not a place where maximum will be attained, and hence we need to maximize q only over those mu which satisfy summation mu I y I is equal to 0. I am not interested in finding value of q mu for those mu for which mu I y I is not equal to 0, for those mu anyway I know is minus infinity. So, we need to maximize q only over these or mu such that summation mu I y I is equal to 0. So, once I take summation mu I y I is equal to 0, the b term drops out. Now, I need to only find the infimum of this with respect to w. That means, I have to differentiate it, find the gradient with respect to w equal to 0, which we already done earlier. So, I know infimum with respect to w is attained at w is equal to summation mu I y I x I, because we just differentiate with respect to w and equal to 0. So, how do I get q mu for a given mu now? For that mu, using that mu, I write w equal to mu I y I x I, and now I substitute in this expression w is equal to that mu I y I x I and impose mu I summation mu I y is equal to 0, then I get q mu, right. Let us calculate q mu. This is what you have to do, you have to substitute w equal to this, and my q mu is this. Now, I am taking away infimum because I know what to do for infimum, I have to just do these substitutions. My q mu is w transpose w, mu I into 1 minus this. I have written as summation mu I and the second term. Okay, the second term mu I y I w plus x square per p. So, this mu I y I b will go to 0 because I have to put mu I y I is equal to 0. So, I have to put w is summation mu I y I x I. So, this w is summation mu I y I x I whole transpose. This w once again this I is a dummy index. So, I put this w as summation over j mu j y j x j plus summation mu I minus mu I y I b has gone, mu I y I write this as x I transpose w, x I transpose w is once again summation mu j y j x j. So, both these summations are same. I have summation of I and j here, mu I y I, mu j y j, x I transpose x j. Here also mu I y I, mu j y j, x I transpose x j. This is minus 1, this is half. So, I will get a minus half. So, q mu is summation mu I minus half summation over I and j, mu I y I, mu j y j, x I transpose x j. That is my q mu. So, my dual now turns out to be maximize q mu, which is given by this as you just now seen, subject to mu I greater than or equal to 0, and we have to impose the extra condition mu I y I is equal to 0. Right? So, this is my dual problem. This is also a constraint optimization problem. The optimization variables are mu. Right? The cost function is this, because my variables are mu. This is a quadratic function. This term is linear in mu. This term is quadratic in mu. So, this is a quadratic function. Constraints are linear. Mu I greater than or equal to 0. Summation y mu I y is equal to 0. So, this is once again a constraint optimization problem with quadratic cost function and linear constraints. The training data vectors x I, x j, unlike in the primal where they appear inside the constraint, they appear only in the objective function. They are also only as a inner product x I transpose x j. Right. And the optimization variables here are mu. How many are there? N, right? As many examples, 1 mu per example. So, there are n examples. So, there are n Lagrange multipliers. And so, the dimensional the optimization problem is n irrespective of the dimension of x. No matter what the dimension of x is, dimension of this optimization problem is equal to the number of examples. Okay. We will just remember these things for later use. So, sum up, the optimal hyperplane is a solution of this problem, this optimization problem. We call this the primal problem. Instead of solving this primal problem, we solve the dual and obtain optimal Lagrange multiplier. This is the dual problem. We solve this dual problem. So, when you solve this, we get all the mu i's, and once we get all the mu i's, this is my final solution. What do you mean by w star b star is my solution? Now, you give me any x, then I calculate w star transpose x plus b. If this is positive, I put it in class plus 1. If it is negative, I put it in class minus 1. So, w star b star gives me my optimal hyperplane. So, from now on, give me any new feature vector x, I will say I will calculate w star transpose x plus b star, and sign of that will give me the class. Okay. As I said, we are considering only 2 class problem. So, this is the full SVM method for linearly separable case. So, we define the optimal hyperplane to be this, then that is the dual and that is my final solution. Okay. Now, in all this we assume that the training data is linearly separable. What happens if the training data is not separable? What do you mean by training data not separable? If the training data is not separable, what it means is there will not exist a W on B to satisfy these constraints. These constraints are satisfied by a WB only if WB is a separating hyperplane. If there does not exist a separating hyperplane because training data is not linearly separable, then there will not be a WB that satisfies the constraint. That means there is no feasible point for this optimization problem. If there is no feasible point for the optimization problem, obviously there is no optimal point. So, if the data is not separable, the optimization problem has no feasible point and hence no optimal no solution, right. Which means in general, if the data is not linearly separable, we can't find the optimal hyperplane by this formulation. So, we need to change this formulation so that we can basically why are we not able to find the solution? Because my constraints may not be satisfied. Whenever constraints are not fully satisfied, the standard technique in constraint optimization is to use what are called slack variables. So, that we will keep our constraints not hard, but soft, so to say, and then we we manage to get a feasible point. So, that is what we will do next. So, what we do is for general case, normally what is that we want yi into W transpose xi plus b greater than or equal to 1. If that is satisfied, forget about the ji right now, we actually wanted yi into W transpose xi plus b greater than or equal to 1 for separation. But suppose there is no WB that can satisfy this. Then I say, okay, if you can't get it greater than 1, get it at least greater than 1 minus ji, right, where ji is some positive number. So, essentially ji measures a penalty of how much you are unable to satisfy your required separability constraint. If I did not have this minus ji, y into W transpose xi plus b greater than 1 is my separability constraint. I am unable to get WB, so that for each I it is definitely greater than or equal to 1. I said, okay, at least get it greater than or equal to 1 minus ji for some slack ji. Now, I do not want too much slack. If I have too much slack, obviously, you will take W to be 0, right, because you want to minimize this, you take W to be 0 and put everything into the slack. So, I do not want too much slack. So, the ji's are the slack variables, I will penalize ji's. So, if ji are large, this term will be large, right. I am minimizing not only half W transpose W, but also summation I is equal to 1 to n ji, right. So, my optimization variables now are WB and ji. Find WB and ji is ji1, ji2, jn. So, that I added the ji's here, but I do not want too much slack. So, I added a penalty here. Okay. So, the first thing about this is that a feasible solution always exists. You give me any WB, I put a corresponding yi and xi here for each of the I. If it is greater than 1, I am fine, I will take ji to be 0. If it is not greater than 1, whatever is the slack I need, I take that into ji. Right. So, any WB is feasible now, because I can always find ji to satisfy this, right. So, there is no problem about finding a feasible point, feasible solution always exists, any WB is feasible. Ji measures the extent of violation of the optimal separation, that also we see. So, basically if ji is greater than 0, then there is a margin error. If ji is greater than 1, xi is wrongly classified, you see. If ji is greater than 0, what it means yi into W transpose xi plus b is not greater than or equal to 1, it might be only greater than or equal to 0.5. Even if it is greater than or equal to 0.5, the sign of W transpose xi plus b is same as sign of y. Right. So, I am not getting the optimal separation, because we wanted so much separation. We didn't want any training pattern between W transpose x plus b is equal to plus 1 and minus 1. That much separation I am not getting if ji is greater than 0. But if ji is greater than 1, that means the sign is changing, which means I am not even classifying it correctly. Right? That is how ji measure the extent of violation. Now, finally, what we are minimizing is my margin plus this some of the slack variables. It tells you how much violation of separation I am doing, and C is a kind of a exchange rate constant. How much of increased margin of separation am I willing to take at the expense of making so many errors in classification, so to say. So, this tells me some measure of the error in optimal separation. So, the C tells you how much of error I am willing to trade with how much of increase in margin. C is user defined parameter, much like regularization constant. Later on we will see that is actually regularization constant. Okay. C is user specified. Okay. So, we can see this formulation. What we are saying is this is W transpose x plus b is equal to 0, this is W transpose x plus b is equal to 1, W transpose x plus b is equal to minus 1. So, I take this to be my W on B. Then, if a class 2 pattern came here, so for all the patterns which are beyond this anyway, my Ji's will be 0. If a class 2 pattern came here between these two, this J would be greater than 0, but less than 1. It's still on the right side, but I am actually counting this as my margin, right, because I have taken this W on B, I am counting this as my margin. With respect to this much margin, this is one pattern that is not giving me that much margin, right. On this side, on the other hand, this pattern is actually on the wrong side of the hyperplane, right. If I want to take this as the separating, so here the Ji would be greater than 1, right. But essentially what it means is, given this pattern is here and this pattern here, normally I would not have been able to find any separating hyperplane. What I decided to do is call these two patterns errors, then I get a separating hyperplane with such a nice margin, right. That is what this formulation is. Suffer a bit of penalty by misclassifying a few patterns and then separate the rest of them, right. That is what I am trying to do. Okay. So, that is my optimization problem, right. Minimize over W, B and Ji. So, I put that as the all the Ji at the bold Ji, half W transpose W plus C times the sum of slack. For I have written this in now my standard optimization thing. In operation, all my constants have written as something less than or equal to 0. So, I wrote it as, instead of writing yi into W transpose xi plus b greater than or equal to 1 minus Ji, I wrote it as 1 minus Ji minus yi into W transpose xi plus b less than or equal to 0. And similarly, instead of writing Ji greater than or equal to 0, I wrote minus Ji less than or equal to 0. This is my optimization problem now. Now, what is my Lagrangian? Once again, my Lagrangian will be a function of the optimization variable W B Ji, and there will be one Lagrange multiplier per constraint. So, there will be n Lagrange multipliers for these n constraints, call them mu 1 to mu n, and there will be another n Lagrange multipliers for these n constraints, call them lambda 1 to lambda n. Then my Lagrangian will be a function of W B, all the Ji's, and then mu i's and lambda i's, right. And Lagrangian will be my cost function plus sum over mu I into this constraint plus sum over lambda I into this constraint, right. So, my Lagrangian will be W B Ji mu lambda, this is my cost function, plus mu I times my 1 minus Ji into yi W transpose xi plus b plus lambda I times minus Ji. So, I wrote it as minus lambda I Ji. So, mu I are the Lagrange multipliers for the separability constraints as earlier for each example, lambda I is the Lagrange multipliers for the constraints minus Ji less than or equal to 0. Okay. So, this is my Lagrangian. So, what will be my Kuhn-Tucker conditions? I have to get derivative with gradient with respect to W is equal to 0, derivative with respect to B is equal to 0, gradient with respect to J, that means partial derivative with respect to each of Ji is equal to 0, that is the derivative constraints. Then I need feasibility, all constraints should be satisfied, and mu I should be greater than or equal to 0, lambda I should be greater than or equal to 0, and there are complementary slackness. So, let us write all our Kuhn-Tucker conditions. First is gradient of W, gradient of L with respect to W is equal to 0. So, as W, the function is still the same, it has not changed. So, I get one W from here and I get mu I yi xi here, right. So, gradient of W is equal to 0 still gives me the same old thing, W star is summation over I mu I yi xi. Similarly, with respect to B, I get the same old thing. What will it give me if I differentiate with respect to each of the Ji's? There is one Ji here. So, I get a C term plus C here, I get a minus mu I from here, minus lambda I from here. So, C minus mu I minus lambda is equal to 0 for each I, which is same as mu I plus lambda is equal to C for each I, right. So, the derivative with respect to the remaining optimization variables will tell me mu I star plus lambda I star is equal to C for every I. Then I have the feasibility constraints. All my Ji's have to be positive, and these are my other constraints 1 minus Ji and Y W transpose Xi plus B less than or equal to 0, separability constraints. All my Lagrange multipliers have to be non-zero, non-negative, and my complementary slackness mu I into this constraint should be equal to 0. Similarly, lambda I Ji should be equal to 0. Okay. These are my full complement of Kuhn-Tucker conditions for this optimization problem. Let us see what this means. W star is still given by the same expression as you already seen. Okay. We also have the extra condition mu I plus lambda I is equal to C for every I, and because both mu I and lambda I are non-negative, mu I plus lambda I will also be non-negative. So, we have this for every I. What does this mean? If mu I is strictly between 0 and C, right, my complementary slackness, remember my complementary slackness implies if mu I is greater than 0, then this term is 0, this constraint becomes equal to 0. Similarly, if lambda is greater than 0, then Ji becomes equal to 0. Right. Now, because I have this, if I consider all mu I which are not only strictly greater than 0, but are strictly less than C, then mu I is greater than 0, the first complementary slackness tells me that the constraint is 0, and because lambda is greater than 0, why is lambda greater than 0? Because mu I is strictly less than C, and I need mu I plus lambda is equal to C. Lambda has to be strictly greater than 0, which implies Ji is equal to 0. Right. So, if I consider any mu I, so that mu I is strictly between 0 and C, then lambda is greater than 0. So, Ji is equal to 0, and mu I greater than 0. So, this term is equal to 0. In this term, I know Ji is equal to 0. I get 1 minus Y into W transpose Xi plus B is equal to 0. So, now the complementary slackness conditions give you 1 minus Y into W transpose X plus B is equal to 0. So, earlier for any mu I greater than 0 this is true. Now, for all mu I which are strictly between 0 and C this is true. Now, this obviously immediately gives me like earlier my B star, right. Only thing is, instead of this formula being true for any mu that is strictly greater than 0, it is only for those mu which are strictly between 0 and C. So, now I can think of my support my vector that determine B to be one that are not stuck at 0 or C. See, now that earlier I had only mu I greater than 0, now I have mu I plus lambda is equal to C, and lambda is also greater than or equal to 0, which means mu I is now strictly between 0 and C anyway. I need to have 0 less than or equal to mu I less than or equal to C, similarly 0 less than or equal to lambda I less than or equal to C. So, and unlike the earlier problem, now mu I also has a strict upper bound. If mu I is strictly between their bounds, not equal to either of the bounds, then that mu I that determines the Xi which are closest to the separating boundary now. Earlier, the Xi that are closest to the separating hyperplane are those whose corresponding Lagrange multipliers are strictly positive. Now, with the slack variable formulation, I have to look at those Xj for whom the corresponding Lagrange multipliers are not stuck at either end. They are neither stuck at 0 nor stuck at C. Those mu's correspond to Xj which satisfy this, which means those are the Xj that are closest to the separating hyperplane now. Okay. Apart from that, once again, if you I can U star and B star, so I am done. So, once again I can use the dual to find the mu's. So, what will be the multipliers. So, now there are the mu's and the lambdas. So, Q is a function of mu and lambda. They obtained as infimum over all the optimization variables of the primal problem, namely W B I of the Lagrangian. Lagrangian function of W B I and the two sets of Lagrange multipliers mu and lambda. So, where the Lagrangian as you already seen is given by this. So, basically for a given a particular mu 1 to mu n and lambda 1 to lambda n, if I want the value of Q at that mu 1 lambda, I need to find infimum of this expression at that mu 1 lambda with respect to W, B and all the Ji, right. Let us first consider finding infimum with respect to Ji. Okay. what is the Ji dependence of this term? For each I have a Ji into C minus mu I minus lambda I term. So, for a given lambda and mu, if C minus lambda I minus mu I is not 0, then I can take that Ji to be as negative as I want when I am taking the infimum, or as positive as I want, and hence infimum will be minus infinity. Because we have this term, because you are taking infimum with respect to Ji, unless we impose C is equal to mu I plus lambda I, infimum will be minus infinity, and that we are not interested. So, once again we only need to look at mu on lambda such that C is equal to mu plus lambda. When we consider mu and lambda such that for each I mu I plus lambda is equal to C, then all the Ji terms will drop out. For each Ji I got a C minus mu I minus lambda I, and similarly all the lambda terms drop out, right. The moment I impose the C is equal to mu I plus lambda I, then all terms containing either lambda I or Ji are drop out of the expression. Once they drop out of the expression, what is left is the old expression, and I need to find infimum with respect to W on B, and we already know that is that old Q function we know, right. So, if you want to find the new Q function, all we have to do is that we get the old Q function only anyway, because we have to anyway impose this, but in addition to the old constraints, I have to also impose the constraint that lambda is greater than or equal to 0 and C is equal to mu I plus lambda I. Because I have to impose C is equal to mu I plus lambda I, my Q function will not contain any lambda terms. So, Q is still only a function of mu. So, I do not have to actually maximize over lambda I, as long as I can somehow ensure that these two conditions are satisfied. These two are easily satisfied by imposing this condition on mu. Once I impose this condition on mu, I can take C minus mu I to be lambda I, because lambda I need not have to, does not appear the cost function, lambda I does not affect the cost function. As long as I satisfy the constraints on lambda I am done. So, let us say I solve it only for mu with mu as this constraint, then C minus mu I take to be lambda I, then I have satisfied lambda I greater than or equal to 0 as well as mu I plus lambda is equal to C. So, which means my dual now will be exactly same as the old dual, the cost function, all the old constraint will be there. Earlier I had only mu I greater than or equal to 0, now I have mu I less than or equal to C also. So, the only difference is an upper bound. Right. This is very nice. See, in the primal problem, the problem is totally different. I get a plus C into summation Ji in the cost function, each of my constraints is changed, I got n extra constraints. So, if you wanted to solve the primal, lots of extra work needs to be done. But if you want to solve the dual, whether I am thinking that these patterns are linearly separable, or I am willing to use slack variables so that I always have a feasible solution, always get a solution. The only difference is whether or not I put an extra upper bound, which is anyway user defined constant. So, I essentially solve this optimization problem, the dual, by just choosing some convenient upper bound on mu, that is all. Right. The only difference is an upper bound on mu. So, that is another reason for preferring to solve the dual. Right. Of course, it is very easy to see this is my primal problem. So, if C tends to infinity, if C is very large, that even a little bit of positive Ji, this term becomes so large that that will not be where the minimum is attained. So, ultimately my minimum will be attained only for those Ji, for that place where Ji are all 0. If Ji are all 0, it is like the whole problem. So, as C tends to infinity, we get the whole problem. As C tends to infinity, I get the whole dual, obviously, right. So, this is my dual. So, we solve the dual, and once again this is given by my this is my optimal hyperplane. The only difference is earlier the B star is for any j such that mu j greater than 0, now is mu j strictly between 0 and C. So, this extra one upper bound on C is all the difference in the optimization problem between solving the problem assuming training data is linearly separable, or taking general data and finding the best possible linear separate. It is best possible in the sense I have just decided to make a few errors on some patterns and add the errors in one specific way by adding the slack variables into the optimization problem. So, this is a formulation which somehow I am minimizing some measure of the error in classification while maintaining a maximum margin. right. When in the linearly separable case, the optimization problem is very nice to see, because it maximizes margin under separability constraint. In this case, because of the C, I am essentially adding apples and oranges. I am taking some part of the margin, I mean some margin plus some constant into the errors I am making, I am minimizing that. Okay. But anyway, this is what one does has to do in general, because in general we have no way of knowing whether the training data is linearly separable or not. Okay. So, by using the slack variables Ji, we can find the best hyperplane classifier. Okay. So, this is the optimal separating hyperplane, very good. So, we can find, instead of finding any linear classifier now, we have a concept of some optimal linear classifier, and we can find it by solving a nice quadratic optimization problem, a quadratic cost function and linear constraints. Okay. The only difference is when we are solving the dual, as we seen, the only difference is upper bound on mu. So, I just throw in a constant C as an upper bound on mu, and I always solve only the dual. So, it is very nice. Of course, as we already seen, the best linear classifier may not be good enough. The idea is we want to learn nonlinear discriminant functions, and recall that the whole idea of SVM is to transform X's into some high dimensional space and then learn a linear classifier. The idea is X's will be transformed into Z's, and then in that Z space you learn a linear classifier, right. So, as just to recall, this is the idea. So, if this is the original feature space and I needed a quadratic discriminant function to separate the two classes, if I map the patterns into higher dimension space, I would be able to separate with a hyperplane. Essentially, this is in the x1 x2 space, whereas this is in the x1 square x2 square x1 x2 space. Right. So, a hyperplane can separate the classes now, whereas I needed a second order discriminant function, quadratic discriminant function in the original space. Here is another example. If I have an XR problem, right, to separate the two classes I need a nonlinear classifier, a single line cannot separate them, but I can always map them into a higher dimensional space, which is x1 x2 on x1 x2, then in that space a hyperplane can separate them. Right. So, that is the basic idea. So, in general we use some mapping phi from m dimensional space to m prime dimensional space. In the new space, my training set now will be Zi yi, where Zi is phi xi. So, we will be in the next in the rest of this class, and also most of our discussions we will use Z and phi x interchangeably. Phi xi will be Zi, those are the new this is the vector corresponding to the training vector xi in the transform space. Okay. So, once we use this phi to transform all the training patterns from m dimensional space to m prime dimensional space, my new training data becomes Zi yi. So, Zi is equal to phi xi. So, we can find the optimal hyperplane by solving the dual. What was our dual? If I wanted to find the best linear classifier, this is what I have to solve, where xi xj are the training patterns. So, nowhere else the training patterns appear. So, if my new training pattern, I have transformed them to Zi's, I just replace xi transpose xj by Zi transpose zj, that is all, right, or phi xi transpose phi xj. So, we can find the optimal hyperplane by solving the dual, just simply replacing xi transpose xj with Zi transpose zj. The dual problem will be what now? I just replace xi transpose xj with Zi transpose zj. Zi transpose zj same as phi xi transpose phi xj. This. Am I done? The good thing about it is that it is an optimization problem over Rn, the number of examples. It has nothing to do with the function phi or m prime, nothing to do, meaning the dimensionality of this optimization problem does not depend on the function phi or the new space m prime. So, originally I may have 100 dimensional space, now phi x may be 10,000 dimensional space, but in both spaces I will be solving maybe a 1000 dimensional optimization problem, because I have 1000 examples. So, the optimization problem remains only of order of n. At least earlier we said naively solve the problem in the Z space, I have to solve a problem of the dimension of the Z space, that is m prime, but now I am not solving that, because I am solving the dual. The dimensionality of my optimization problem remains n, the number of examples, it does not become m prime. So, even if m prime is 10,000 or 1 million, my dimensional optimization problem does not increase, it will stay at n. This is the good thing, but does it mean that I have really got rid of computational cost? Of course, during learning I have to solve this problem to find mu I given all my training examples. So, to calculate phi xi transpose phi xj. Of course, I can pre-compute it because these do not depend on the optimization variables here. So, I can find all the n square ordered n square numbers phi xi transpose phi xj one time and then solve use those constants here and solve this optimization problem. Of course, still it can be expensive because I have to first transform each of the x's through phi xi, phi might be a difficult transformation, and in that high dimensional space, maybe 10,000 dimensional space or 1,000,000 dimensional space, I have to calculate the inner products. But I do it only once and then solve this mu. Is that all? No. What do I do with the mu's? I have to use my W stars. So, the W star will live in the phi x space. So, W star is the same dimension as phi x. So, I have to store W star, the 1,000,000 dimensional W star, and every time now you give me a new x, I still have to do W star transpose x, right. I have not. So, every time I use the classifier, I suffer the computational cost of going into high dimensional space and finding inner products there. Of course, in addition, even though the operation problem remains of dimension n, I do not know because effectively I am learning a hyperplane in a very high dimensional space. Are 1000 examples enough? The second problem we will solve much later, but this SVM method will efficiently tackle that, but we will see the reasons for it later. But right now, let us concentrate on the computational problem. How do I get rid of having to do this phi xi transpose phi xj? Okay. The basic idea is the following. Suppose we have a function which takes pairs of m dimensional vectors and gives me a real number such that k of xi xj is phi xi transpose phi xj. Okay. We call such a k as a kernel function. What do you mean by I have such a function? Of course, I have such a function. Once I know phi, I can define k xi xj to be phi xi transpose phi xj. Our basic idea is that such a function is less expensive than calculating phi xi transpose. We may not have time to look at kernel function in this class, but not to make a big secrecy of it. For example, if I take k xi xj to be 1 plus xi transpose xj whole square, 1 plus xi transpose xj whole square needs one extra multiplication compared to xi transpose x. Suppose xi transpose xj is 100, xi is 100 dimensional, xi transpose xj needs 100 multiplications. 1 plus 1 addition we do not care. 1 plus xi transpose xj whole square will need one more multiplication. Right? So, we are looking at kernel function like that. We will show square as a kernel function would be phi xi transpose phi xj for a phi which effectively lends the quadratic discriminant function in the original space, right. So, what we considered right in the beginning 2 classes ago about mapping x1 x2 to x1 square, x2 square, x1 x2, x1 x2 and then finding a linear classifier there, where we said we need order n square dimensional z. Finding an inner product in that space would be like 1 plus xi transpose xj whole square. We will see that later. So, in that sense, instead of doing 10,000 multiplications to find phi xi transpose phi xj and also many multiplication to actually find phi xi and phi xj, we will just do one extra multiplication than xi transpose xj and done. So, we are looking for functions which are not particularly more expensive than doing xi transpose xj. Let us say such a function exists. Let us just assume for now that such a function exists. Then what can that function give us? Then replacing z A transpose zj by k xi xj, we can solve the dual. This is my dual. Phi xi transpose phi xj is k xi xj. So, I will just instead of phi xi transpose phi xj, I put k xi xj here. So, k xi xj is much less computationally expensive than phi xi transpose phi xj, which means I have solved at least the computational problem of calculating phi xi and phi xj's while learning the mu's. Okay. So, replacing z A transpose zj or phi xi transpose phi xj by k xi xj, we can solve the dual without ever computing any phi xi. So, at for obtaining the optimal hyperplane, right. So, one problem is solved now. So, I can efficiently solve the dual. See, that is the whole idea why we went to the dual. If I want to do the same thing in the primal, this xi will become phi xi, right. So, I can't use the kernel function here, and this is not even linear constraints anymore, because there were phi xi there, right. I mean, of course, it will be linear constraint in the sense phi xi are constants linear in W and B. Even though there is a linear constraint, this phi xi, because it comes into the constraints, right. Every time I do I use any numerical algorithm, in every iteration I have to calculate the corresponding phi xi in the primal. On the other hand, in the dual, because it comes only as xi transpose xj and nowhere else, I am able to substitute this by the kernel, right. So, what the kernel has given me is that by replacing this phi xi transpose phi xj by k xi xj, I have been able to efficiently solve the dual problem without actually calculating phi xi and obtain all my hyperplanes, all my Lagrange multipliers. Okay, so far so good, but does it mean that I have solved the problem of inefficiency inherent in this idea? One of the inefficiencies inherent in the idea is every time you give me a new pattern to classify, I have to transform it into this high dimensional space and then classify it with the corresponding name. So, even though for obtaining my mu's I do not have to calculate phi xi, what do I do with my mu's? Ultimately, I obtain my mu's so that I can calculate W star, and I calculate W star because next time you give me an x, I have to calculate phi x transpose W star to classify it. So, W star stays in my million dimensional space. So, I have to store W star and I have to calculate phi x every time you give me a new x and do this. What do I do about this? Well, as it turns out, I do not have to do that also. Okay. It is very very interesting thing. Let us say mu I star are the solutions of the dual. Then we know that W star is summation mu I star yi phi xi. Okay. So, for example, what will be B star? We see in B star will be yj minus phi xi transpose W star. Now, W star is given by this. So, it will be yj minus summation over I mu I star yi phi xi transpose phi xj. Wherever phi xi transpose phi xj comes, I know I do not have to do any phi x phi j computation. I can convert it into kernel function, and k xi xj is much less expensive than phi xi transpose phi xj. So, for example, to compute B star, I do not need to calculate phi x's at all. If I know all the mu stars, then I can just put k xi xj here and calculate B star. Of course, B star is not the only thing I need much more than B star. What do I have to do? Given a new pattern, what do I have to compute? I have to compute fx, right. Ultimately, my classification is dependent on the sign of this fx. What is this fx? Z transpose W star plus B star. What is Z? Phi x. So, phi x transpose W star plus B star, that is what I have to calculate and find its sign. What will that be? So, W star, I write it as W star transpose phi x, W star is mu I yi phi xi. So, this is summation over I mu I star yi phi xi transpose Z is phi x plus B star. Now, I know how to write B star. So, this is summation over I mu I star yi phi xi transpose phi x can be written as k xi comma x plus yj minus summation over I mu I star yi k xi comma xj. This is for a particular j for which the corresponding mu j star is between 0 and c. As you can see, while finding the mu's, I do not have to calculate any phi x's. After obtaining the mu's, you give me any new x and I want to calculate its actual phi x transpose W star plus B star. Once again, I do not have to calculate phi x at all. I can do with the kernel functions. I just have to calculate this, right. This is a really interesting way of learning nonlinear classifiers. Now, no matter what phi x is, no matter what how high dimension m prime is, I am solving a constraint optimization problem, that to a quadratic cost function, linear constraints, constraint optimization problem, whose dimension is simply number of examples. And to solve this, I do not have to actually calculate my phi x's. Phi is only in the background, is only effectively, because I canalize my inner product. So, while solving the dual, where phi xi times the phi xj would have come, I would put k xi xj. I solve the dual, get all my mu's. Once I get my mu's, I have to effectively calculate this, that I can calculate like this using my mu's and the kernel function. So, I never actually calculate W star, never actually calculate phi x for any x, right. It is an interesting way of learning nonlinear classifiers. We solve the dual whose dimension is that of n, the number of examples, and all we need to store are all the non-zero Lagrange multipliers mu I star and the corresponding support vectors xi, right. All xi corresponding to mu I star greater than 0, I have to solve, if I solve them, if I store them, you give me any nu x, I calculate this and then I am done. I can classify any x by doing this. I never need to enter the phi x space, even though I am actually using some transformation inside phi which maps my m dimensional space to some other high dimensional m prime dimensional space and finding a linear classifier there. I never calculate phi x for any x. I never ever enter that m prime dimensional space, right. The only connection between that space and me is the kernel function. Somehow to find the right kernel function. We will see next class how we can find kernel functions, but provided that I can find a kernel function k xi xj is equal to phi xi transpose phi xj, such a way that k xi xj is much simpler to calculate than phi xi transpose phi xj, then I am done. So, no matter what is the transformation phi I am interested in, if I can properly find a kernel function to represent it, then I am done. Right. So, what is the final support vector machine idea? Is that I obtain mu I stars by solving duals where that xi transpose xj is replaced by zi transpose zj, which is replaced by k xi xj, that is essentially choose a suitable kernel function and use a penalty constant C if needed. Using a penalty constant is simply putting an upper bound in solving my dual optimization problem. So, I will just throw in a C and choose some suitable kernel function. We will see what are suitable next class. So, and I solve the dual. Once I solve the dual, I store all the non-zero mu I stars and their corresponding support vectors. Now, that is my support vector machine. This represents my classifier. How do I represent my classifier? Once I solve them, I am now ready to work. You give me any new pattern x, this is what I calculate and I classify it by the sign of this. So, if we have a suitable kernel function, we never need to calculate phi x for any x. What does this mean? For all I care, the range space of phi can be infinite dimensional. I never go there. Okay. So, this is a very, very interesting idea of effectively finding a linear classifier in a high dimensional space. So, next class we will look at the kernel functions, what kernel functions are suitable and how different kernel functions will allow you to find different nonlinear classifiers. Okay. Thank you.